Okay, cool. So let's get going. So last time we talked about data science ethics in broad strokes, and towards the end, we started focusing on fairness in particular. And even more, we zoomed in on one particular story that was in the news a few years ago. And we're going to bring up some actual data for that story and look at it more closely. The reason we're going to focus on this one example is that we're going to be able to glean some important general lessons from this example. So we'll be able to think about ideas that are applicable in many contexts through the lens of this particular example. And I want to say, as I alluded to last time, some of these lessons I think are likely to be pretty, how's there going to be a theorem in an ethics class? But we'll see that it's actually directly relevant and interesting. And this might be, as I said, a little surprising if you're used to thinking of fairness or equity or data science ethics questions at large as sitting really on the opposite end of the certainty spectrum from mathematics. But as I said, we will be using some code. So like last time, let's start up our Python session as we continue to go. So just to get everyone caught up from last time, as a refresher, so Compass is commercial software that is intended to predict recidivism, and it's used in court systems in the United States as a part of sentencing processes. And this system was analyzed in 2016 by a nonprofit public interest newsroom called ProPublica. And what they discovered is that if you look at the predictions that this algorithm makes, then if you focus in particular on the defendants that are later found not to reoffend, you find that the model predicts Black defendants at a high risk for recidivism at a much higher rate than for white defendants. And on the flip side, if you look at the people who do end up reoffending, the model is more likely to say for one of the white defendants that they're low risk, and it's less likely to say it for a Black defendant. So within either group, you have adverse outcomes being disproportionately borne by the Black defendants. And the model does this even though race is not a variable that's available to the model to use. And we're going to look a lot more closely at that today. I'll ask a question first that I asked last time to make sure that everybody's on the same page with this part. So you might just remember this from last time, exact same question. But does the Compass model satisfy the equal treatment notion of fairness? In other words, if you change only a defendant's race while keeping all the other variables the same, does the model produce the same output, yes or no? The class recollection is strong on that one. The model isn't using race as a variable. By definition, what that means is that the result doesn't change if we only change the race. So, if you imagine actually needing to change the spreadsheet, imagine you have a spreadsheet that you're using as input for this model, you would go in and you would do nothing. There's no race column, so there's nothing to change. So the model sees exactly the same stuff. However, equal treatment, as we discussed last time, is not the end of the story. If it were, then we could just check, hey, are they using race as an active variable in the model? And if they're not, we'd be done. We could move on. But what we want to do is drill down and understand why the model is exhibiting these biased results, so we can start to think about the problem in a more constructive way rather than just shrugging our shoulders and moving on. So before we get into the data, I want to ask you to sort of commit to one of these two possibilities, and we'll see how things unfold. So if you recall the story's coverage back in 2016 and you followed it on social media, you probably saw a lot of takes of the story that involved advocating for dispensing with this model, getting rid of this organization as someone that we funnel money to through public coffers because the model exhibits these biases. And it's a big and complex story, but I want to focus on one particular part of it, which is based on the ProPublica results that we've talked about so far. We have disparate impact for the model predictions. Which of the following do you think reflects what we're going to discover when we look at the data more closely. So option A is that problems with racial bias are direct evidence of corruption, because if they had done their job properly and trained a good model, they would not have had any racial bias in the model? Or do you think option B, problems with racial bias in models cannot be eliminated simply by firing bad people? Which of these do you think most accurately reflects what we're going to discover? There's unanimous agreement on this one. Everyone is selecting option B. So that is going to be the case, as we're going to discover. But rather than just stating that, I want to make it really vivid to you. So we're going to use some mathlets here in a minute. We're going to build our own models, and we're going to see exactly what's going on here. Because I think this problem is, it's a nice one because it was in the news, but also the data are extremely clear when you sort of distill out what's going on with this model. It's actually all very comprehensible. So let's start by looking at the data, though, and we're going to grab it from ProPublica's GitHub organization. So I don't want to walk through this code that carefully, but maybe just at a glance. We're going to import pandas. That's the Python data frames library. If you don't know pandas, you want to invest a little effort in learning it between now and the beginning of the semester, because it's a hugely important library when you do machine learning, really in general, because Python is so important, and it is the data frames library for Python. So this is the URL that it's stored at, and what we're going to do is read that CSV in using the pandas.read CSV function, and then we're going to select only specific columns. So we're supplying a list of columns here to this index operation so that we're only grabbing certain columns out of that data frame. So you could do this without the brackets here and look at the whole data frame if you like. And then just to simplify the analysis, you get this score for recidivism, but we want to simplify it. So it's a decile score. So it runs from 0 to 10 or 1 to 10 or something like that. But we're going to simplify it and just say high risk is if it's bigger than 5 and low risk otherwise. That will make it just easier for us to talk about the data that we're seeing. And what we're going to do here then is group by 2-year recidivism. So this is actually whether the particular defendant recidivates and the race, and then aggregate by average. So we're going to see on average for each of these pairings, for all the people in the data set, what the risk score is. And let's take a look at that. Yeah, so if you don't recidivate and you're an African-American, the model on average rates you with a 34% chance of being high risk. So that means of all the people in the data set who didn't recidivate were African-American, 34% were listed as high risk. And for the Caucasian candidates, sorry, I keep saying candidates, I don't know why. For the Caucasian defendants, it was about half, actually less than half that, about 15%. And it's flipped around the other way for people who do recidivate. You can tell the model is doing something. It is true that the rates are lower here for the people who didn't recidivate, and they're higher for the people who did. So the model is somehow generally oriented in an appropriate direction. But when you start looking at the racial breakdown here, you see some other patterns. Also, one nice thing about looking at the data set directly instead of just reading a report is that we can see things like there are other races that are represented in the data set. And you do see a lot of variance here with those other races. You probably want to look at how represented they are. There could be some noise there. But in any case, I do advocate for looking at actual data when you can, instead of just relying on someone else's report, because you can kind of see things that they can obscure in the way that they write up the report. In any case, as we said last time, there's a really big discrepancy in both of these categories. So we want to start to look at that more closely. So I want to get some contributions here. So based on what we've seen so far, I showed you this data set. We talked about this result that you see in this particular table. Are you satisfied that this analysis conclusively demonstrates that using this model introduces racial bias into the system? What other considerations would you like to see weighed before you came to that conclusion. Okay, so several nice answers here. This one is really on point. So Hardy, do you want to elaborate your answer here? Yep, that's great. Yeah, that's an excellent answer. That's very, very much foreshadowing what we're going to get to here. And I'll just share a comment that came in a little bit earlier that's directly relevant to what Hardy just said and what we're discussing now, which is that the model inspection process where you're asking, hey, how is this model performing? And what are the causes for any issues that might come up in what we see and how it performs? That is sort of nominally, it's just you're trying to make sure that the product that you're producing is satisfying the constraints that you want it to satisfy. But it also opens up avenues for research. You can explore these questions, try to understand why things are the case. And as we're going to see, that's actually really important for ultimately addressing the problems that you're seeing with the model. So I want to share what I had prepared, because there are just a number of issues to kind of keep in mind here. Think of this as looking forward to Data 2080, when you're going to be able to explore each of these in more depth. But there's a whole menagerie of possible things that you would really want to investigate to understand this thoroughly. Like, for example, where did the data come from? How was the table created? What was the process that determined the values that go into each column in the original data set? Has there been some pre-processing done by someone who's already made some judgment calls about how the data should be analyzed? And does that potentially impact the results that you're going to get? So that sort of points 1 and 2 here. Also, the way that we got the data, is it subject to some transparency? Is there some possible, incentive misalignment in the way that the data set is produced? And then point 4 I have here is very much what Hardy was driving at, which is this observed bias introduced by the model, or is it reflective of the underlying data in some way? Are we sort of shedding light on a broader underlying problem, or are we looking at something that's an artifact of the model that we can sort of excise if we're careful enough? So in general, there might be different answers to that. Here, there's going to be a pretty conclusive answer, as we'll see shortly. But then also another option here, or another facet, is there a less biased model available? And also, what happens if we abandon the model? So a lot of times you see people say, look, algorithms can exhibit bias. Solution, eliminate algorithms and run on human judgment. But if you've checked in at any point in the last forever, then you know that humans also have biases, and we can be pretty bad about the way that we practice them. And also, human brains are not super inspectable. We don't really know what our brains are doing when we make judgment decisions, especially snap judgment decisions. There's a lot of inscrutability in that process. So it's not necessarily just a solution to throw out algorithms and say, let's look at all problems through the lens of human judgment. It's more, the problem really is more fundamental than that. So in any case, I've sort of alluded a lot to that. We're really leading up to what I hope will be a really insightful way of looking at this problem. I do want to just briefly touch on these first couple of points. So Data Responsibly has a Colab notebook, which does the data processing here. And so you can look into that if you want to see it in more detail. Also, ProPublica published their analysis in their GitHub repo. So I think that in this case, there's not a lot in the way that the data were produced that is ultimately salient to the analysis. So we're going to skip over it. But it is something that, if you're really taking this seriously and giving it kind of full attention, then little oversights or misinterpretations early on can really just destroy an entire analysis. So you do need to be careful about that. So what we're going to do is move on to explore some of the other questions, because I think those are the lessons that are more readily generalizable to other examples. And let's start with item number 3, which is transparency. So in fact, the Compass model is proprietary. They're selling this to the government. They're looking to continue to make money off of it. And if they exposed all of the details about how they do everything, their concern is, why would they pay us then moving forward? So they keep that a secret. And we can't really, therefore, say, like, what is the model doing? We can't use the model internals as a way of trying to get at this problem. And I want to ask a general question about that. So do you find it objectionable that criminal justice decisions would be made on the basis of a proprietary algorithm? This one or some other one, set that aside. The general question: criminal justice decisions being made on the basis of a proprietary algorithm, even, let's say, hypothetically, one that exhibits no objectionable biases. So that's a strong assumption, but make that assumption and still decide whether you think algorithms should be used in this way. So several folks are finishing typing up some nice answers, so I'll just give folks a little more time to wrap up. Okay, so I'll summarize what we have so far. So 3 answers here suggesting, yes, there's something intrinsically objectionable about basing decisions that really impact people, particularly vulnerable people, in a way that is not subject to any sort of inspection. That's objectionable. And then there's one answer kind of offering a different take, which is that there are other potential avenues you could use to address this. For example, someone could monitor the algorithm, sort of a responsible third party could be charged with monitoring the algorithm under the protection of an NDA. And that could be sort of a way to balance the consideration of the company needing to stay profitable and the process has like some accountability. Or we can inspect the results. So, that's what we're doing here. We don't see the internal process, but we can see the results that the algorithm produces. And that can be, from a certain point of view, could be considered enough to satisfy the due process constraint. So yeah, those are different takes. Personally, I would tend to lean towards this first cluster of answers, because as an individual in the system, if you're given a harsh sentence because of an output of some model, it's going to feel pretty hollow if someone says, well, look, in aggregate, we've looked at this and it seems to be pretty fair based on certain demographic slices or whatever. You don't know if it's somehow, combining 2 or 3 variables about your life in some idiosyncratic way and kind of glitching out and producing this weird result. You wouldn't be able to say because you can't see what the model is doing. So in any case, that's a kind of legal, moral question that you could spend a lot of time on. I just want to sort of prime your intuition about that there's something here that really warrants some consideration before you even account for what the model might actually be doing or whether it has biases. So, okay, so anyway, we can't look at the actual model. It turns out in this case, it's not really going to matter for reasons that will become apparent shortly. So now we'll get into the part that I've been sort of preluding for quite a long time now. I'm going to give you an actual mathlet. And it's gonna take a second to load. It's a little bit of a heavy mathlet. But anyway, it's a scatter plot showing a random sample of 250 defendants. So the actual data set is too big to fit into this mathlet. It gets very noisy, but we'll get the same idea with just these 250 sample points. So the attributes plotted are number of priors and age. So number of prior convictions for that particular defendant along the horizontal axis and age of the defendant along the vertical axis. And the recidivism is indicated by color. So teal means after 2 years we observed and this person did not reoffend, and orange means this person did reoffend. So you can guess that these variables are fairly predictive at the extremes. Like if you've had more than whatever the number is here, 15 or 16 priors, there are only 4 people with that many prior convictions, but they all recidivated. And maybe that's not surprising. You have someone who's been convicted over a dozen times. The chances are good that this isn't their very last time. And then likewise, if you're, in your 60s or 70s, then okay, there's this one person here that recidivated, but otherwise these people are mostly not going to commit crimes again because they're old, and it's just less likely when you're old to commit crimes. We're going to consider just a very simple model here. So we want to avoid the risk that there's going to be, some kind of sophisticated neural network that's doing who knows what with the features. This is simple as it can be. there's a line separating the ones you're going to predict as orange and the ones you're going to predict as teal. And you want it to do a good job. So play around with that a little bit. You know, if you put it way over here and predict everyone as teal, it's 57%. If you predict everyone as orange, it's 43%. You can do better somewhere in the middle, but don't forget, you can also change the slope of this line. So you have two handles on the line. I just want to see what people are able to come up with in terms of accuracy for this model. So this is as simple as machine learning is ever going to get. You just grab the line and you stick it where you want. All right, as people mess with that, I want to share this one, which does a pretty good job. So it gets about 69% accuracy on this particular data set. So let me try to replicate that here. Where's the other one? Or like pretty much goes through the origin. So let's see. Yeah, it looks pretty good. I'm trying to remember if you can do a little better over here. By the way, what we're going to do in Data 1010 is basically mathematize this. So instead of just doing it with a mathlet where you're dragging things around and you're like, I don't really know if I have the best one, we're going to like tighten up this model for one thing, put a little better objective function than just like straight up accuracy, and then show how you can use numerical methods to perform this optimization in a more rigorous way. So that's an aside, but in any case, I think the one Jason found here is actually better than the one I came up with by a percent or so. But anyway, if you can get around 67%, then that's pretty good. Not only that, it's basically the same as the actual full-fledged COMPAS model. So whatever thing that they're doing that they're charging a bunch of money for, you just did effectively the same thing by dragging this little purple line to wherever you felt like it should go in this little scatter plot. And that's not dependent actually on the amount of data. You're going to get very similar results if you have a lot more data. 250 is large enough that we're already looking at, you know, pretty much the same structural phenomena that we're going to see with the full data set. So I think that's a little harrowing. I mean, already that's an interesting question. Why are we spending taxpayer money on this model, which is basically doing the same thing that all of us just did now? And by the way, you did it in your little mathlet, like you're a master's student, but you totally could have done this when you were in like middle school, elementary school. This mathlet could really be plugged into any educational curriculum without concern that it's going to lose people. And yet the accuracy is essentially the same as this model that we're paying money for and we're worried about the bias of. But in any case, to sort of take the conversation in a little bit of a different direction, we sort of have to feel like if you think of the model sort of extracting information about race and then using that to make predictions in a way that you want to subvert, you would think, well, okay, this model is as simple as it gets. We literally just drew a dividing line in the plane, and that means we must be eliminating racial bias. So we should use this model instead of whatever COMPAS is doing, and everything's going to be fine. As you can probably guess from my tone, that's not how it works out. So I'll give you another version of the same mathlet, and you can experiment with this and see for yourself what it's going to take to produce a result that's not biased. So I'm showing here the percent of Black non-reoffenders that are misidentified by your line, as well as the percent of white non-reoffenders who are misidentified. And so the thing that you want to avoid is this top number being much bigger than the bottom number. And in the initial placement of the line that I have here, that's the case. But I want you to sort of move the line around to some reasonable places where you know, more or less where you had it before, and kind of see how these two numbers change together. Okay, so Hardy found a line here that actually is pretty close. So you can move this purple line way up. so that you're, so let's see, down here a little bit. Yeah. Maybe up a little bit. Yeah, there's somewhere in here where you can get it. Oh, here we go. There's like a very specific line that you can actually get very similar percentages here. But also you're really, the model is doing very poorly now. You have available to you a model. And remember, this is really bad. This is someone who's not going to reoffend that you're saying, yeah, I think they're a very high recidivism risk. They should have a long prison sentence. These are people spending years of their life in prison unnecessarily. And you have available to you a model which does that misclassification, like sort of maximizes overall accuracy, and does that misclassification at a more of like a single digit or low teens rate. And instead you have to, move the line up and start misclassifying lots and lots of people in order to try to get these numbers closer together. And at this point, your accuracy is so bad that really a judge shouldn't be relying on that data. It's not fair to anyone for judges to be relying on sort of high risk predictions that don't actually predict high risk at all. I mean, this is less than half of the time you're actually getting it right, when you could get it right way more than half the time. So the bottom line here is that there's not really any sort of sensible place for this line to go. If you wiggle the line sort of in a minor way around the general vicinity of where it should be, then this top number is always quite a bit bigger than the bottom number. And you could maybe do a little bit better by accounting for these numbers in your objective function when you fit the data. But ultimately, you're going to have a problem even if you do that, unless, as I said, you throw caution to the wind and don't care about it misclassifying at all. Of course, you could also move the purple line all the way up so that everyone is predicted to recidivate. And then now it's 100 in both. That's definitely equitable from a racial point of view, but it's also the worst possible outcome for everyone. So my hope is that by doing this stuff through mathlets instead of through like training some scikit-learn model or whatever, it becomes really clear that the bias is present in the data. In fact, it's present in these two variables. If you just look at number of priors and age. So if you just look at number of priors and age, that's enough to already give us some serious problems. So just as a kind of comment that we alluded to earlier, so you would think like, okay, we need to rely on human intuition to kind of get away from the bias exhibited by these models. That has been investigated. So there was an experiment done where they gave the same data to humans and asked them to predict whether a person would recidivate or not. And humans are on par with the COMPAS algorithm and the two variable model that we just looked at, just putting the line in there ourselves, both on accuracy and on racial bias. So you have all three of these things: human judgment, the more sophisticated, presumably, COMPAS model, and this very simple two variable model that we just fit with our eyeballs. These are all producing very similar results on both metrics, overall accuracy and the racial bias. And the way in which the data were presented to the humans is through one paragraph summaries that the humans read, and race was not disclosed in those paragraphs. So that might be surprising if you aren't used to thinking about these kinds of problems. I think by this point in the discussion, it's maybe not surprising to you, but this is something that in the news coverage needed to be highlighted because it wouldn't be obvious to people that that's even possible. Okay, so let's skip ahead a little bit in the script to this question, which we're going to look at in the actual data momentarily, but I want to give you an opportunity to speculate, first of all. So what do you think is the mechanism by which racial bias manifests in this data set, even though we only have these two variables, age and number of priors? How is the model somehow producing racially disparate results just out of those data. So I'll share the answers we have so far. Several other good answers are coming in, and feel free to complete those now. But yeah, you got it. So age is presumably not in any way related to race in a way that would be showing up in this data set. You know, your age and your race are uncorrelated. But the number of priors is not. So the number of prior convictions that an individual would have is a result of a huge variety of inputs. So including potential racial bias in how people are arrested, potential racial bias in how people are convicted, but also socioeconomic realities and a wide variety of other possible factors that you could consider if you were studying this problem in great detail. And you would really want to understand that in order to think about how to factor prior convictions in to the data set. But once you have decided that prior convictions is a legitimate thing to base these predictions on, then already you're just definitely going to have racial bias in the way that the model produces its results. Yeah, so I'll just share some of the other answers that were typed later. Oh, so Katie is making an interesting point here. So maybe what I said about age is a little too glib. It's possible that there's some bias in how people show up with respect to their age in the data set. That's true. There might be some role that's played in the filtering process to determine how age is reflected in the data set. So yeah, it could be either. It's definitely prior convictions though. So just kind of summarizing that, the fundamental issue is that the number of prior convictions is correlated with both race and recidivism. So in using the prior convictions variable, the model is also picking up on the race variable that it doesn't have access to. So as you can imagine, Northpoint, which is the company behind Compass, responded to this analysis. It got a lot of attention. It was obviously very bad press for them. And they said, look, our model is fine. They're looking at the wrong thing. You shouldn't look at, did someone reoffend or did they not reoffend? And then based on that particular group, each of those groups individually, look at the racial breakdown and how the model makes predictions. What you should do instead is look at all the defendants in a given risk score. So instead of slicing people up by how they either recidivate or don't, you should split them up by how the model predicts they'll recidivate or don't, and then see, is the model prediction actually accurate for that group of people, even when we break it down by racial composition. So we can see what they're talking about here in the data set with this little pandas command. So we can do df.query and just select out the people in the data set who are either white or black, and then group by the model score, decile score, and race, and look at the 2-year recidivism and aggregate by mean so that we can see the whole data set distilled down to a few numbers. So for example, if you get a score of 1, so the model will spit out a number, so it is 1 to 10. And if the model spits out a score of 1, then empirically there's a 22% chance or 20% chance, whatever these numbers are quite close together. So roughly a 20% chance that you're going to recidivate. And that is true whether we condition on whether you're white or black or not. And the same with all of these others. If you look down, they're quite nicely calibrated. Within each decile, the risk of recidivation is about the same, or recidivism is about the same. And there's a little bit of noise, but this is within bounds that you would expect just based on the statistics. And by the way, that's another thing we'll look at in data 1010 more carefully. We'll talk about when you see differences in numbers, how can you tell whether it's sort of close enough that it's just noise that's the difference, or there's actually a meaningful difference there. But anyway, Northpoint put forward this table and they were like, look, our model is fair. If it were to say for everyone that we gave a risk score of 3, if you look within that group and actually, you know, the black people are actually much less likely to recidivate than the white people, that would definitely be unfair, right? You're telling a judge, here's this risk score, use this to make a decision about this person's prison sentence. And in fact, there's racial bias in that result where, actually, if you're Black, you're less likely to recidivate, and you're white, you're more likely. That means that those people are being treated more favorably by the justice system if they're white than if they're Black. And that's definitely also a problem. So yeah, I got one message ahead. I'll just share this message as well. This is just what we said about this condition that North Point is describing, and it's called calibration. So we say that a model is calibrated with respect to a particular demographic breakdown if the values in this table, each pair that you look at here for a particular output, are about the same. Yeah, so ProPublica could have looked at the data in this way instead of the way that they did look at the data. And they could have said, look, this is a problem. Look at how, if the model says this person is high risk, they're actually not as high risk if they're Black as if they're white, and this is not good. This is something that we need to try to address so that these people are being treated more fairly. And that's definitely a mathematical subtlety. Are you slicing by model score, or are you slicing by actual outcome and then breaking down by groups from there? It's not something that people are fluent enough in when they think about manipulating data that they would necessarily even recognize the difference. So ProPublica publishes this story with this other take, this calibration take, rather than what they did look at, which is actual outcomes. It's not clear to me that even a macroscopic percentage of the readership is really going to notice the difference between those two things. They're going to have the same feelings about how the algorithm is unjust, and we need to do something about it one way or the other. And hopefully I've convinced you that these are both reasonable fairness criteria. You really don't want it to be the case that when you're making these predictions, there's a strong racial bias either way that you slice it. And so what's the answer? Well, let's just hold ourselves to the highest standard possible. We need to come up with a system which is fair in both ways. So either way you slice the data and then you break it down by demographic groups, you should get similar values. However, it turns out that this is simply not possible. So it is mathematically impossible. And this is not just for an algorithm, but for any decision-making system, any configuration of data. Sorry, it's actually not quite true if it's any configuration of data. For very special conditions on the data set, you can achieve this, as we'll see in a second. But in general, for the kinds of problems where it is going to be an issue and you're trying to hold yourself accountable in this particular way, it's actually mathematically impossible to do that. So I want to state this in a way that highlights exactly what the obstacle is. So we're just going to state it in a general framework, as is befitting a mathematical theorem. So we'll replace group membership we'll replace race in the North Point example with group membership. So we'll call them group A and group B, and we'll replace recidivism with outcome. So we'll have positive outcomes and negative outcomes. So A, B, positive, negative. Those are our sort of, the combinations of those are our four possible groups that we're going to consider. Okay, so here's the setup. So we're going to have a collection of individuals, each of which is either in group A or group B. And each individual is going to have an outcome which is observed to be either positive or negative. And we're going to assign each individual to a risk bin in such a way that the following basic notions of fairness are satisfied. So fairness by risk score, meaning within each risk bin, the proportion of positives is the same among the two groups. And also fairness by outcome, which says that among the individuals observed to be positive, the average score assigned to members of each group is about the same. So, and this also needs to be true of the negative individuals as well. then here's the conclusion of the theorem. If the proportion of positives among group A is not equal to the proportion of positives among group B in the data set, so that's a property of the underlying data, it either is true or it isn't. And if it's not, then the only assignment of both conditions, the only risk bin assignment that satisfies both conditions is the one that assigns a risk score of 1 to every positive individual and a risk score of 0 to every negative individual. In other words, if your data set is already conducive, then fine. Or if you can manage to make absolutely perfect predictions of each outcome, that's also fine, and nothing in between. So otherwise, if you can't do one of these two things, then you're definitely going to violate one of these two fairness criteria for any group, any split into two groups, A and B. So stated another way, the two notions of fairness are incompatible unless one of these two simple conditions is met. The base rates are equal for the two groups, or we can predict outcomes perfectly. And it's worth emphasizing, although I mentioned it already, this theorem doesn't put any constraints whatsoever on how the assignments are made. So it could be a sophisticated model, a very simple model. It could be a judge, a jury, or pure randomness. It really doesn't matter. The same conclusion applies. There's no discussion of algorithms here. This is any bin assignment at all. So we might not have time to walk through this whole explanation. I'll leave it in the notes so you can go through it if you want, but we do have time to start. So there's a sequence of mathlets here to kind of walk you through this. So suppose that we have two risk bins, risk bin 1 and risk bin 2, and we have 13 individuals, and all of the group memberships, the outcomes, and the risk bin assignments are illustrated in the figure. So we've separated them by risk bin, but then we've also indicated, well, are they group A and are they positive or negative by putting that information here. So this is an individual that was in risk bin 2, happens to be in group B, and was positive. So we can look at this data from sort of two different perspectives. So the one on the left shows just each individual in their risk bin, and the one on the right puts each individual into a quadrant based on its group membership and outcome. So all the A negatives, you can see there are two of them here and here, they go into this top left quadrant. And similarly for all the other ones. And we've indicated the individuals instead of putting like A minus, because that'd be redundant. It's already implied by which quadrant it's in. We show the risk score for each individual based on the risk bin that they fall in. So for example, here you have a half for this particular A negative, and you have 2/3 for this A negative. And similarly for all of the other ones. So yeah, so this part is illustrating kind of where the numbers are coming from. So we have two, so if you click this show button, so we have two A's in risk bin 1. And that's telling you that this A positive corresponds to this particular entry here. So it's a half because there's one negative and one positive in that particular group in that risk bin. And so we put a 1/2 here for this person. And similarly for all of the other ones, you know, as we were pointing out, A negative is 1/2 because there's one A negative and one A positive. This 2/3 comes from the fact that there are 3 A's and only one of them is negative, and so on. So I'll just sort of allude to the proof of this theorem that we're going to get into. So I didn't explain this very thoroughly. It's going to be broken down more carefully in the subsequent messages. It comes from a particular journal article that's linked here. So you can see that in the journal form. I really tried to break it down though with these figures and mathlets. There's some more mathlets coming that will help you understand exactly what's going on here without kind of getting into math proof vocabulary quite as much as in the journal article. But the bottom line is we're going to look at this square and kind of slice it different ways and figure out mathematically that there's a fundamental trade-off between these two notions of fairness, just based on the fact that they're looking at the same data but slicing it in different ways. So the risk bin assignment slices it horizontally. Are you group A? Sorry, the the risk bin assignment slices it this way. So are you in this bin or are you in this bin? Whereas the positive negative assignment looks at, are you in this column or are you in this column? And you can see that, you know, ultimately you're looking at the same collection of individuals in both figures. And the fact that you're slicing the same data two different ways is going to establish a mathematical connection between the two. And I think it's like just the right amount of mathematical difficulty. Like there's enough that it's interesting, but there's no advanced math. It's all kind of basic algebra and, you know, just manipulating variables and averages and stuff. So anyway, I'm going to leave it there. So that's all I have for today. And this is the last day for the summer. So thanks for participating. This was a lot of fun for me. I hope that it was fun and useful for you. I hope that it's useful for the people who check in later, you know, as the semester starts and folks want to get caught up. Of course, there's always the content to revisit. So all these videos are going up on YouTube. The links are being shared at the homepage. So if you haven't gone there yet, the homepage is available, just 2 clicks in the top left, and there's course homepage linked. And from there, you can get all of this stuff, all the videos, including from Tuesday. That video is live now. You know, everything else, the data gymnasia links. So anyway, that's it. Thanks a lot. And I'm looking forward to seeing everybody in September.